the speed over mean. But like I said, when we actually deal with this, all these energies, this is actually more common. Root mean square speed. Okay. So V mean. And then then there is another that speed that you can think about. If this is a speed distribution, there is a moment that at this speed, there's something special about this speed. Right? This is a 1, this is number 2, and it's actually this is number 3, which is what we call the most probable speed. That's number 3. There are 3 different ways that I can do the error. Because this is a distribution function of probability, and I can calculate mean value, root mean square mean value, or this is what is called the MP, means most probable. Most probable speed, which is this one, right? This is most abundant. And how do you going to mathematically calculate that? And this is the form that I can use the integral. The reason is, you guys know that when you have a function, the slope is 0 here, right? So therefore, slope of your distribution function at V is V most probable is what? 0. That's the 0 slope right there. So those are the 3 values. So we are talking about now V mean, V RMS, V most probable, okay? It's kind of involved, right? It's quite complicated. But this is a way because it is your V has this the probability has a distribution, and there are 3 different ways easily you can find out, and they have a different values. And this is a VNP, a little bit bigger, and we can use it even bigger, and that is that's a mean, and this is V RMS. So RMS is a little bit bigger than the V mean, and the most probable is the smallest, and this one is 2RT. Mean value is 8RT at root mean square. 3, and the mean value is 8RT. Because I have an exact math formula, so I can derive using this equation, I can come about those actually exact values. And once I have that, I can really calculate the real value. I never been close enough to say anything about the real gas. So I can just finish up from here. Okay. So once again, I'm saying the same thing here. If I do any kinds of, let's say I'll just do the root mean square 1 proportional to n t, r or rt. Once again, mass times velocity square is a constant when you're keeping the temperature to be constant here. So on the average in this gas, so this is really the conceptual piece, and it's not actually macro pchem, but the Atkins book like to give a molecular sense, because we're going to talk about real gases in the next class. And in this room, we are measuring the temperature. And temperature is, let's say, 25 degrees C, or 298 Kelvin. Does every gas has the same temperature? No. We are measuring only one value, which is an average value. But gas has a moving at different speed. They have a different, in a way, temperature, different kinetic energy. They move around. But we only measure it as an average value. And that's actually good enough for us to define the internal energy and calculate enthalpy, entropy, and other thermodynamic variables. But in real life, it's a mess, okay? It's a mess. And if I give you guys, okay, what about O2 32 grams per mole, right? And then you guys can calculate. So this one is actually, I do want it to 0.032 kilogram per mole. So I can use a kilogram, and I can use this one as a joule per mole Kelvin unit, 8.314. That's right. And then this is a unit of Kelvin, and you put it in. You guys will calculate actual speed. And I'm telling you that if you put these numbers, this number is actually enormous. Okay? Because when you put a temperature of 300 Kelvin, think about it. This is like 8, right? This is something pretty small, which is in the bottom, so it's a big number. So this, whatever you're gonna choose, this is a huge number. And like I said, when it comes down to calculate it, it was like 1,000 miles an hour. And there are even something more higher than 1,000 miles, and there's something moving slower than that. The last comment that I want to have is now, I'm going to draw the two curves here. So this is a real complicated story, but this is the whole detail. So this is the whole, like how fast they are moving it. This is a one gas. This is another gas. Which one is hydrogen and which one is oxygen? Which one moves faster? Right? The one that moves faster, right? That must be a hydrogen, that must be an oxygen, right? All right. Another one, same thing. This is the same hydrogen or same nitrogen, and which one is 1,000 Kelvin? Which one is 500 Kelvin? 1,000 Kelvin is higher energy, right? So this is a higher energy. This is a lower energy. Right? I just give you this kind of the representative number that is something like 1,000 miles an hour. I just keep on saying that number. That's just the room temp, happen to be a room temperature, like a nitrogen or an oxygen. But if you have a hydrogen, man, that's like, I don't know, something like 10,000 miles an hour. Okay, but you don't need, because they move faster because they. And if you increase the temperature, they move faster too. This is just a more complicated picture, and there is some section called the statistical thermodynamics, and there's actually individual components and you sum it together, and that's another section that different class will. Thank you.